Welcome back to Learning Solidity. Now in today's tutorial we'll be addressing a topic which is subject to a lot of debates, and that is randomness within Solidity, or more specifically the Ethereum network as a whole. Now even if you go to the official documentation of Solidity, there is a topic called security considerations, under that pitfalls, and under that private information and randomness. Now I want to highlight a line in this which simply states, using random numbers in smart contracts is quite tricky if you do not want miners to be able to cheat. And this is kind of an important thing because a lot of the randomness within Solidity is driven off blocks, and obviously blocks are basically generated by the miners. So you can manipulate things to a certain degree if you control a large enough mining cluster. But I'm not going to go into that too much. What I will do is basically cover a few concepts which I've come across. Now I didn't come up with these concepts. This was a collection of concepts I discovered browsing Reddit and Stack Overflow, and I will give credit and also links to the original creators in the description box down below. So the first thing we're going to do is we are actually going to create a very basic random function which is not really safe to use within Solidity if we're going to do anything like sort of gambling or sort of like anything that depends on financial randomness, because this does not work. This is more if you wanted to create a very simple game that has no monetary or no sort of cryptocurrency value behind it. And this is just a very basic concept of randomness. So within Remix, what I've got already is a contract called random, and I'm going to just basically use two mechanisms that the block basically, or the block global variable, allows me to do, and that's essentially the block hash and also the block number. Now what this does is hash the given block only works for 256. So okay, let's go and first create our function, and let's call this unsafe block random, and that returns, that's public and returns a unit. Now all this is going to do is just return a random number between 1 and 10. So what we're going to do is return, if you remember, we actually want to return something that's going to be a hash of the current block number. So this returned bytes 32. Bytes 32 can actually be cast to an integer because obviously it's the same size as a uint 256. So what we need to do is, because we're actually casting that, we need to do a cast to uint. I'm not sure if you need to cast to uint 256. We'll see if an error crops up. We can call then the global variable block dot, I think it's just block hash, yes it is, block hash. I'm just going to spell it right. Now what we need to pass into this is again a uint. So what we need to do is look for block dot number. Now if I'm correct, this has got to be within 256, so we've got to do -1, and then all we're going to do is simply state modular 10, and that should actually basically say, okay, divide by 10 and up until the point of where we have a remainder that can't be divided by 10, and return that remainder. So let's just have a look at this in action. So we've got our random unsafe block. So let's create the random. Let's clear this. Let's first generate a random number. So we've got 6. Let's generate another one. We have 0. Generate another one. We have 2. Okay. So that is basically safely generating a random number. So essentially what we're doing is using this or this whole sort of number as our seed to base our randomness off. So this can obviously be expanded if, for instance, you want it out of 100. So let's clear that again. Recreate random. Let's actually get rid of the first one. Nope. Go. There you go. And that's 66. 60, 32. As you can see, it generates a random number based loosely off the block number. Okay, so what we can do there, we can expand on this a little bit more. Now we can add a little bit more randomness to it, and like I said again, this can be manipulated so it's not truly random. We can use the similar concept here, but also add something to it. So what I kind of mean by that is, instead of generating a random number off a block, we can generate a random number based off, say for instance, an incrementing value. But again, this is something we can pre-predict. So again, we're going to call it function unsafe increment random. That's public and returns a unit. Sorry. So what I mean by that is we're going to define a private, actually, a unit private base. So what we're going to do is the same sort of similar concept, except we are also going to basically SHA it, or hash, shall we say, the actual value. So what I mean by that is returns a unit, SHA3, which is our hashing function, base increment plus plus, so I'm going to increment it each time, divisor 100. What's that complaining about now? And have I done that correctly? 2, 3. Oh, there we go. So what this will do, in theory, will generate again a random number each time I actually call it. And again, it's not really random, it's actually random based off an incrementing value. So every time it's called, it will produce a different effect. So as you can see, similar to the first function, it's producing a random number. So this is probably the worst case scenario. I would never do that. That's always just a really bad way to do it. Now I want to address, before I go on to my final solution, which is a bit more involved, the Oracleize implementation of the randomness, because they don't really have a true implementation of randomness. What you can do is use the Oracleize library, and what the Oracleize library does is it will send a request to a contract. This contract will basically then pick up your request. Say for instance, if it's a HTTP request, you can make it to obviously a random number website such as Wolfram Alpha, if I'm pronouncing that right. I'd say like get me a random number between 1 and 1,000, and then that will return it. And basically what Oracleize will do is then make that request from their servers, then their servers will basically pass that to the contract will then pass it back to your contract callback method, and then that will obviously trigger the random number generator. Now obviously there are some limitations with that. Now that's basically implying that we trust Oracleize. I'm not saying they're untrustworthy, but when you start having to trust solutions such as Oracleize, you basically become dependent on them. Now for instance, if they had any network issues or they shut down their service, you're now at a loss. So that's something you want to try and avoid personally, unless this is a solution that's sort of supported by yourself. And there is actually, another thing that I could add to this, but again, it's not something that the community often trusts, is that what you could do is you could make a call to a contract and supply your own random number. Now the only issue with that is that it could be subject to scrutiny, scrutiny. I can't even think of the word here. Basically, they will scrutinize your implementation. They will believe that you are potentially manipulating the outcome of the random number. Say if this was a gambling website for your own benefit. So that's always something to bear in mind, that when you're actually generating random numbers, having this visibility in the contract that you are not having any input of it gives a lot of trust. This is again why Oracleize sometimes can be seen as a very good solution, because it's a trusted layer where you have no control over, but you are entrusting them that they are providing a valid result. Okay, so the final thing that I want to actually sort of do now is I'm going to generate a little sort of like random casino. So what I'll do is I'll create a new contract, call it casino. Yes, I do want to name that. Right, one of these days. Now we'll call a contract. I'll call it casino. Okay, so in our casino, we want to be able to enter a lottery. Okay, so our lottery needs some basic functionality. Now, the key functionality of a lottery is going to be buying a ticket and also checking the result. To really enforce randomization, you kind of have to add a third step to this. Now the third step is verification. So what you need to do is first add boundaries to each step. So for instance, let's create our first function, and that's going to be buy ticket. It's going to be payable. It's going to be, we start public first. It's public, it's payable, and I'm also going to say, actually no, because we only got one function, we don't really need a custom modifier for this. Public payable and returns a boolean. Okay, so what we're going to do is state, for instance, that the buy period, or the buy ticket period, is available from, let's say, private buy period equals, let's just say 1,000. Obviously you wouldn't specify it that explicitly, or if you did, you'd say basically append 1,000 onto the current timestamp or the current block, or whatever mechanism you want to do to measure a length of time. So we're going to say the buy period is 1,000, then the uint private verify period is 100 because we want a short verification period. Uint private claim period equals again 100. Obviously you might not want a claim period limit, for instance, so let's just use that as a very loose example. Okay, so when we're buying a ticket, what we want to do is ensure this state of randomness. So this is again a concept that I didn't come up with. Again, I'll give you a link. This is my interpretation of this whole concept. I've actually modified it slightly to try and ensure a true state of randomness. So when we buy a ticket, we want to specify a number, like you would with a lottery ticket. You'd specify your number is, and then obviously you'd buy your ticket. We need to ensure that our numbers are basically protected, because if people can see what numbers we have, then they could either pick, obviously they can then manipulate certain aspects of this to ensure that either we don't win or various other bits and pieces. Now, the way that I would preferably like to have a value passed to buy ticket would be simply a case of uint and then hash. Now what essentially the hash is a combination of, say, two things. It's your number, or numbers, in this case it's only going to be a single number, and what's known as a salt. Now, because we're creating a hash, obviously if we have a limit of numbers between 1 and 100, picking, obviously, deciphering a hash is very simple. Is 1 equal to your hash, is of a hash value of 1 equal to your hash now, 2, 3, so forth. That's why you imply a salt, or it often referred to as a secret. But because each of the transactions on the Solidity network are publicly accessible, you don't want to pass the number or the secret at this level. You want to do it from an external level. So for instance, this is just a very crude example. So let's just say function, let's say generate hash, and what you do here is create a uint, and that would be our number, and then a uint, and that will be our salt. And that's public. Let's just make it payable because we're actually going to pass it onto the buy ticket mechanism just as a show. And now I want to highlight this. This should not be part of the contract, because this is what we want externally. We don't want this internally. So returns, well, because we're just going to use it as a relay mechanism for now. But like I say, do not use this as part of a contract, because the transaction will be publicly accessible. All the data passed to this, the number and the salt, will be passed. Now obviously, like I said, you can call this salt, you can call this secret, or whatever. As long as it basically passes, it's okay. So at this point now, what we're doing is we're returning buy ticket, and we're going to generate our salt, our hash from our number and our salt. So all we're simply going to do is state uint SHA3 number salt, and that is basically our ticket. So we're actually sending by ticket a hash of it. Basically it's a load of jargon because no one can really understand or decipher what that is, because we've generated that from two completely random values. So if I'm right, I don't know if I've passed in SHA3. Warning is deprecated for KECCAK. Probably should use that instead. KEK. 256. Yeah, you go. Now I'm not sure if it does pass two values, but we'll leave it as that for now. Or you could do something as simple as that is plus that. So we know that that's always going to generate our random value. And we should always make sure that our salt is something correct as well. So when we buy a ticket, we're simply going to state, well, we're going to need a couple of things. We're going to need a mapping of people that have purchased a ticket. So we're going to need a mapping of address to a uint, and that's simply going to be a list of tickets. Then we're going to need something to basically address as map, because obviously a map is not iterable, so we do need to have a reference point to everyone who's currently in the lottery or the casino. So let's call this address array and entries, and that should be okay for now. Now I'm actually going to add a third and call it address underscore verification, or verified, just to make things a little bit easier. So with our entries, all we're going to simply do is tickets. Let's first do some basic things. So require, because we're just going to assume that you need to it's 1 Ethereum to enter this. Require 1 Ether is equal to message.value, because you have to pass in 1 Ether to enter the lottery. Require that you can only enter the lottery once. So tickets message.value is equal to 0, because obviously, is that correct? Oh no, message.value, so that should be message.sender is equal to 0, because they shouldn't already pre-exist in our lottery. And now let's simply add some basic things. So tickets message.sender is equal to our hash. We also want to add the entrant as well. So entries push message.sender. Okay, so now we have entered our lottery. Now the next thing that we need to do is verify. So what I have forgotten to do is add our block limit. So it's just a very basic example. If something very simple like let's just also create a very basic sort of time period as well with this. Uint private, let's just say start, and we'll also create a constructor for the starting point of this. So function casino public, and the start is just simply block dot timestamp. So what we're going to use, I know this is not a very good way to verify within periods, because obviously, like mentioned previously, the blocks can be easily manipulated. So if the block dot timestamp is less than the block dot time, or the should I say start plus the by period. Actually, we'll make that require as well. Require, because then we can refund things. If the require the block dot timestamp is less than start dot plus by period. Okay, so within shall some comments, correct amount, and let's just call this 1 entry per address. Now obviously you could create a couple of addresses there, but either way, let's just use this as a very basic example. That's something we can't limit. What does it complain about there? Yeah, as obviously again it's highlighting that can be block.timestamp can be influenced by the miners to a certain degree. So let's just bear that in mind as well as part of this. So the next point is our verification. So what we're going to do is call this simply verify ticket. Now this is the point we now want to pass our number and our salt. So number, uint, salt. Now the reason we're passing this in is because we now want to verify our hash. So let's make this public, payable. Actually, we don't need to make this one payable, and returns a bool. And I forgot on the previous function to return true. So simply return true. You don't have to return anything. I always think it's good practice just to confirm that everything's worked okay. So this part of this verification is now to verify that our existing hash is the same as previously. Now I've already got this functionality here, so what I'm going to do is actually extract this. So I'm going to create this function called function. Call this. Actually, I'm going to change that to unsafe entry. Call this generate hash. Pass this to here to make that external, and I'm going to make that pure. Because we're not modifying states, we basically I'll probably should do a tutorial on view and pure. View is basically state that we are not modifying anything within the instance, we're just viewing, and pure means we're not modifying or reading anything within the instance, and we're simply generating a value of two values passed in, so we can make it external and pure. And then we're simply going to return a uint. Okay. So all we're simply doing, we only need to pass in the two values, int number uint salt. So that is simply going to be return that. Okay, now it's going to be moaning. I'm going to be using generate hash number salt. Okay. Why is that complaining? Undeclared a variable. Yes, because it's external, we need to state this. Okay, so this is a local function. Never use function calls in the same country. Only could use more gas than local calls. That is fine. Actually, it doesn't need to be. No, we can actually leave this as public. But this is pure as well, and we can get rid of this. Okay. So the next thing that we're going to do now is verify our ticket. So the first part of the verification is going to be check that this is within our time scale. So we actually have two parameters that we need to pass here. So it needs to be more than or equal to the byte period, and also less than the start plus byte period plus verify period. I could probably have done a better way to store that, but I'll leave that as is for now. Let's also check that this person has an entry more than 0. Let's just cover all the basics. As a valid entry. I'm just putting some comments here for these requires just so people can understand exactly what they're for. And then the final one is validate hash. So simply to validate a hash, all we're going to do again, require. I like using require because it refunds the gas consumption. It basically reverts the transaction, which basically alleviates load off the network. So for this one, what we're simply going to state now is generate hash number and salt is equal to the tickets message sender, which should, if I'm correct, be the hash that we passed in. Now obviously if you circumvented this method, you would have done this externally, and therefore the hash would have been generated outside the application, and all we're doing is verifying the hash generated outside the application is equal to the hash generated in the application as well. Okay, so now we have verified all the basics of essentially everything that we need to do. We can simply state that we want to generate a like a seed, should we say, for generating random numbers. Now I know that this is still potentially flawed, I'm not going to go into details why, because I think people are actually using this as a valid way to generate randomness, and obviously if people are, I don't want to expose what I've discovered about this, so I'm just going to leave it at that for now. So with our verification of our ticket, what we're simply going to do now is create another variable, and this is, I'm just going to call this simply our seed. So uint private winner seed. Now essentially the winner seed is going to be an exclusive OR. So we're going to start with the winner seed. Now the reason we're using exclusive OR is a way that we're constantly inverting values, and that's a great way to kind of ensure that it's so hard to manipulate and predict, essentially predict the next value, because obviously you've got to time everything together. So what we're going to do is have winner seed exclusive OR actually no, we're going to use the salt instead, and to add a bit more security to this as well, to stop people from trying to manipulate without like a salt or something like that, I'm going to also require the salt to be greater than the number. This just protects people trying to manipulate things. Now obviously you can still manipulate the two in a certain degree, and I'm also going to make sure that the number is, no, we'll leave it, we'll let them pick 0 as well. So is the salt or exclusive OR, and then we're just going to simply state uint and then message.sender, because it's kind of hard to manipulate an address within Solidity, so it's purely based off your own address. Okay, so we've got all those exclusive OR statements. So we've now verified our ticket, and we also need to verify now that we have verified our ticket. So let's simply state verified message.sender equals 1. Let's just say that they're verified now. And what's wrong with that now? Message.sender, this is convertible types to uint to oh yes, because it's actually an array, isn't it? Dot push. So I'll push right. Message send. Okay, now we have a winner seed. So once this period's now passed, let's just say function check winner. So uint, actually don't need to pass anything at this point. We're just going to say public and we're going to return a boolean. Okay, so now what we're going to do is add a little bit of a check to verify if a winner has been generated, and what we're going to do is simply bool has winner. I can also make that private. Okay, so in our has a check winner, what we're simply going to do is state, and we also need to make sure that we are beyond the winner timescale, so no one can manipulate this, because obviously we're allowing users to make all these calls, so we're not stopping anyone from making any of these calls, so that is always something to be mindful of. So we now need to make sure that we're equal to or greater than the winner period. We're also less than the start plus by period plus verify period plus win, or what was that? What have I called the last one? Claim period. Claim period. So from that, we are then stating that we verified the timestamp is correct. We also need to require no. Actually, we'll leave that in because that actually does need to be checked every time. And let's just simply state, no, I think that should be sufficient for now, because the rest we're going to enclose. So if no has winner, we're actually going to generate one on the first call, but after that we're no longer going to be able to generate the winner. And what we're going to do is simply also have a winner as well. Now obviously this is only allowing you to actually run this lottery once, so for instance if you wanted to create a contract each time, or if you wanted to generate random lotteries each time, you would have to reset all these values I'm currently setting. Now as winner, okay, so what we have now is we have a winner seed. So what we're going to do with our winner seed, we're actually going to take a little bit of the logic we had from our first two random functions. We already have the seed, which we know is a uint, and we're simply going to make this very simple and simply state winner is equal to verified winner seed let's just, because that should be a very random number, modular verified length, and that should pick us a random winner. And all we're going to do is basically we've got a winner, and we're going to add something like a actually we've got a map, mapping address units, and then just call that, these should both be private winnings. Okay, so with our winnings we're going to take a little bit of a cut because we're the casino. Winnings is going to be winner is equal to, let's just say, actually for now we'll just include everyone because it just makes it a little bit easier. Winner equals verified dot length. Actually we'll minus 10 because we're the house, so we want to claim a little bit of a fee back. So they've won everything essentially in that, and then simply just check at the end, return message.sender is equal to the winner. Oh. And then simply add a final function claim, and that is going to be public. And all that's simply going to do is set the winnings, nope, didn't copy it all, to 0. Let's just put require 0 is greater than 0, just to cut down any unnecessary calls. We're not going to have a claim period. I'm actually going to change that to check period instead. And don't forget to add the comments for that. As winnings to claim. And then we're simply going to send message.sender as winnings, set the winnings to 0, and simply send them. We probably should have done that before we set to 0. Transfer those winnings, and that should be ether. Yeah, because we're essentially minus that times that by the ether, which is correct, yes. So we're going to send them the winnings and then set the winnings back to 0, and there we have it. And that in a nutshell is a way of utilizing randomization within Solidity. And obviously you've got to add a few extra steps to ensure that randomness is actually achieved. This isn't by far nowhere near perfect. Don't just take this and publish it as an actual casino, because you will get exploited if I've missed anything, and it will come at a cost to you. So if you are going to go down the steps of actually writing something like this, ensure you understand everything. Consider all of your options when addressing randomness, because someone will probably figure something out that I have not already figured, and as well as someone's probably figuring something out right now that the whole community hasn't already figured out, and that will basically make this completely redundant. So always consider your options. Like I said, consider your oracle eyes, consider being an actual trigger based casino. Don't ever use the block number or the increment number that I showed you for a casino. That's a definite no. And with that being said, I'm going to wrap this up here because this is kind of a long tutorial, but either way, I hope you found this useful. If you did, give it a thumbs up and a like. If you have any feedback or questions, feel free to leave them in the comment box and down below. And if you want to keep up to date with all my latest videos and tutorials, hit the subscribe button and you will be notified every time I do a release. Now, with that being said, I hope you found this useful. Good luck, and I'll catch you next time.